Previously, we have looked at fluids on the molecular scale. However, in engineering, we are more concerned with the properties of the fluid mass and not the actual molecular interactions. We focus more on the macroscopic point of view rather than the individual responses of the molecules comprising the fluid. We now introduce the term continuum. When we first hear this term, we may think of the word continuous. In classical fluid mechanics, a fluid is defined as a continuous distribution of matter that fills the entire region of space that it occupies. But first, what condition must be present so that a fluid can be classified as a continuum? Now we'll talk about the Knudsen number, which is a quantity that helps us determine which formulation of fluid dynamics should be used to model a situation. Either statistical mechanics, which relates to the fluid's microscopic behavior, or continuum mechanics, which is our focus in this video. Knudsen number is given by lambda, or the mean free path, divided by L, or the length scale of the container. Mean free path refers to the average distance traveled by molecules between collisions. Typically, for the continuum assumption to be valid, Kn must be less than 0.1. So to get small values of Kn, the mean free path of the molecules must be significantly shorter than the length scale of the container. This means that there are more molecule-to-molecule collisions than molecule-to-vessel collisions. When this condition holds, the fluid and container can be considered as one continuous body. We can liken this phenomenon to something we've probably experienced before. In the Admiralty MTR station approaching rush hour, there are many passengers waiting to get on the train. From the time-lapse, we can see that there are more person-to-person collisions than person-to-train collisions, and that the passengers resemble a continuum when entering the train. Now, what are the implications of the continuum hypothesis? Each fluid property is assumed to have a definite value at each point in space. Thus, properties such as density, temperature, and velocity can be expressed as continuous functions of position and time. So how is the continuum theory applied in biomedical engineering? We know that blood is made up of plasma and cellular components, which are like the fluid's particles. However, when studying blood flow, we treat blood as a continuum and imagine it to look like the image on the right. To summarize, point 1. The continuum assumption holds if the calculated Knudsen number is less than 0.1, the mean free path is significantly smaller than the length scale of the container, and there are more molecule-to-molecule collisions than molecule-to-vessel collisions. Point 2. As a consequence of the continuum assumption, fluid properties can be written as continuous functions of position and time. Thank you for watching.